Hello students, welcome to the video class for the subject Power Electronics and PLC, and the subject is for 5th semester Electrical and Electronics Diploma Engineering students. So today we will start with the ladder diagram in PLC. So in the previous class we already discussed about the relays, and normally in real example I told you about the relay, how the relay works. See, this is your in real example, this is your relay circuit. Here three real world parts are there: switch, relay and bell. So this is switch, this is relay and this is bell. So whenever the switch closes, we apply a current to a bell, causing it to sound. So this relay circuit will be now replaced with PLC. Okay, so let's use a PLC in place of relay. So how PLC is used in place of relay, and and rang the bell by using the switch. This is all we need to study. So the first thing that's necessary is to create what's called a ladder diagram. So today we will discuss about the ladder diagram, description of contacts and coils in the normally open, normally closed, energized output, latched output, branching. In all these stages, in all these states we will study, we will describe about the contacts and coils. Okay, so see what happens here. We have to create one of these because a PLC does not understand a schematic diagram. It only recognizes words. It only recognizes codes. PLC, what we need to do, we have to convert this schematic diagram into ladder diagram, and then this ladder diagram converted into codes or programming or coding. Okay, so most of the PLC have software which convert ladder diagram into code. So see, ladder diagram, your there are three steps: first step, second step, final step. So in first step, translate all the items we are using into symbols the PLC understand, and the second step is we must tell the PLC where everything is located. In other words, we have to give all the devices an address, and the final step is we have to convert the schematic into a logic sequence of events. So what happens in the first step? Here our example, real relay example, that is the bell example. Okay, by using relay, how we ring the bell. So in first step, the PLC does not understand terms like switch, relay, bell. So it prefers input, output, coil, contact, okay, etc. So it does not care what the actual input or output device is. It only care that it has an input or an output. Okay, so first we replace the battery with a symbol. This symbol is common to all ladder diagram. Okay, so we draw what are called as bus bar. Okay, this is our bus bar. So these simply look like two vertical bars, one on each side of the diagram. Think of the left one as a positive voltage, the right one as being ground. So further think of the current flow or the logic. Okay, current flow or the logic as being from left to right. Okay, then next we give the inputs a symbol. In this example we have one real world input, that is the switch. So we give input that the switch will be connected to the symbol shown below. This symbol can also used as the contact of a relay. This is your symbol of contact. This is contact symbol. Okay, so next we give the output a symbol. In this example we use one output. Here our output is the bell. So we give the output that the bell will be physically connected to the symbol shown below. This symbol is used as coil of the relay. So this is the coil symbol. Okay, So the AC supply is an external supply. AC supply means this is based on this schematic diagram. We will draw a ladder diagram. Okay. So the next one is here the AC supply is an external supply, so we don't put it in our ladder. The PLC only cares about which output it turns on and not what's physically connected to it. So the second step, what happens in the second step, we must tell the PLC where everything is located. In other words, we have to give all the devices an address. Okay, so in second step we have to give address. So where is the switch going to be physically connected to the PLC? How about the bell? We start with a blank road map in the PLC town and give each item an address. Okay, so see, could you find your friends if you didn't know their address? You know they live in the same town, but which house? The PLC town has a lot of houses, that means inputs and outputs, but we have to figure out who lives where, what device is connected where. This is we need to know. So we will get further into the addressing scheme later. So the PLC manufacturers each do it in a different way. So for now, let's say that our input will be called 4 zeros and our output will be called 500. Okay. So in final step, see, convert the schematic into a logic sequence of events. Okay. So the program we are going to write tells the PLC what to do when certain event takes place. So in our example, we have to tell the PLC what to do when the operator turns on the switch. So this is your ladder diagram. So here this is the, for battery, this is the two bus bars. This is the contact, this is coil, and this is end. And this is the address for contact is 4 zeros, address for coil is the 0500. Okay. And see, final converter diagram, we eliminated the real world relay from needing a symbol. Okay, so basic instructions. First one is the load. Okay, so see, first instruction is the load. The load is represented by LD. Instruction is a normally open contact. It is a normally open contact. It is sometimes also called examine if on. Examine if on. It is represented as XIO. As in examine the input to see if it's physically on. Okay, examine if on. The symbol for a load instruction is shown below. This is the symbol. Okay. So this is used when an input signal is needed to be present for the symbol to turn on. Okay. When the physical input is on, we can say that the instruction is true. When the physical input is on, we can say that the instruction is true. And we examine the input for an on signal. Okay, so if the input is physically on, then the symbol is on. So on condition is also referred to as a logic 1 state. Okay, so the next instruction is load bar. This is the next instruction, load bar. So the load bar instruction is normally closed contact. This is normally closed contact. It is sometimes called load not or examine if close, represented as XIC. As in examine the input to see if it's physically closed. Okay, so the symbol for load bar instruction is like this, normally closed contact symbol. Okay, so this is used when an input signal does not need to be present for the symbol to turn on. When physical input is off, we can say that the instruction is true. Okay, here when the physical input is on, we can say that the instruction is true, but in case of this, when the physical input is off, we can say the instruction is true. Okay, so for this we examine the input for an off signal. If the input is physically off, then the symbol is on here. Okay, So see, physical state off means it is true. So logic it is 0. And when the physical state on, then instruction false, then logic is 1. Okay. So with most PLC, this instruction load or load bar must be the first symbol on the left of the ladder. Okay. Then the next instruction is out. The out instruction is sometimes also called an output energize instruction. The output instruction is like a relay coil. This is the symbol. Relay coil symbol, it is same as the relay coil symbol. So when there is a path of true instructions preceding this on the ladder wrong, it will also be true. When the instruction is true, it is physically on. We can think of this instruction as a normally open output. Okay, it is like a normally open output. And the next instruction is out bar. The out bar instruction is sometimes also called an out not instruction. Out not instruction. So the out bar instruction is like a normally closed relay coil. The symbol is like this, normally closed coil, relay coil. Its symbol looks like that. This is the symbol. So this is one simple example. See, one battery is connected, its plus is this, minus is this, switch W1, SW1, switch SW2, then this is a coil, relay coil. So this schematic diagram need to convert into ladder diagram. In the above circuit, the coil will be, this is the coil, will be energized when there is a closed loop between plus and minus terminal of the battery. We can stimulate this same circuit with a ladder diagram. This is the ladder diagram. Okay, see, this is the for battery, this line drawn, this is plus, this is ground line, this is contacts for switch 1, contact for switch 2, then for the coil, this is the relay coil symbol, and this is end. These two are the inputs and this is your output. Okay, so a ladder diagram consists of individual rungs just like on a real ladder. So individual rung means, see, this is this is your ladder and these are the rungs. Okay, so similarly here, this is a ladder, this is the bars, these are the bars and these are the rung. Okay, so ladder diagram consists of individual rung just like on a real ladder. Each rung must contain one or more input and one or more output. The first instruction on a rung must always be an input instruction, and the last instruction on a rung should always be an output or its equivalent. See, these two are input here and the last one, this is the output. Okay, so notice in this simple one rung ladder diagram, we have created the external circuit above with a ladder diagram. Here we used the load and the out instruction. Some manufacturers will require that every ladder diagram include an end instruction. This is the end. This is the end instruction. On the last rung, some PLC also require an ENDH instruction on the rung after the end rung. So next we will trace the registers. Okay, need of register is to give address to all the input and output. Okay, so see, in this ladder diagram, in the previous example, change switch SW2 to a normally closed symbol, load bar instruction. This is load, this is load bar, this is switch 1, this is switch 2, this is coil. So switch 1 will be physically off and switch 2 will be physically on initially. The ladder diagram now looks like this. This is the address given here, 4 zeros, 0001, 0500. Okay, so switch 1, we assume that switch 1 will be physically off and switch 2 will be physically on initially. The ladder diagram now looks like this. See, for register 00, this means this is the register, this register, for this register. Okay, so for register 00C, at 00 switch 1 is off and switch 1 is on, so this is 0, this is 1. And for register 05, 05 means this one is the 05. For 05 it is 0 because it is off. Okay, so we gave each symbol or instruction an address. This address sets aside a certain storage area in the PLC data file so that the status of the instruction, that means true or false, can be stored. So see, this is the input output register logic bits. So see, this is switch 1 load, then LDB. So these are the possible cases, and for these cases the register logic bits, the logic states for the different switches and coils are presented here. Okay, so A-level application. Okay, see, this is one application or one example is given here to understand the ladder diagram. Okay, dispensing oil from tank. These are all the description for the dispensing oil from tank. This is the ladder diagram for the above given schematic diagram. Okay, so here it is a program scan. This is scan 1, scan 2, scan 101, 10. These are all the possible scans. It is not needed. Okay, so the next one is the counter. What is this counter? A counter is a simple device intended to do one simple thing, that is count. There are up counters, they only count up 1 2 3 like this. These are called CTU. Okay, this is your CTU, count up. And or also it is named as CNT, C or CTR. So there are down counters are there also, they count only down, that is like 9 8 7 etc. So these are typically called CTD. Okay, so to use counters we must know three things: where the pulses that we want to count are coming from. Typically this is from one of the input, like a sensor connected to input 40 for example. Okay, so how many pulses we want to count before we react? Let's count 5 widgets before we box them for example. Okay, so when and how we will reset the counter so it can count again. So after we count 5 widgets, let's reset the counter for example. Okay, this is about the counter. This is pulse, reset. Okay, so in this counter we need to input. Okay, so 1 goes before the reset line. When this input turns on, the current accumulated count value will return to 0. The second input is the address where the pulses we are counting are coming from. So C=X is the name of the counter. If you want to call it counter 000, then we would put C000 here. So this 5Y is the number of pulses we want to count before doing something. Okay, so see, this is a ladder diagram. Here counter is connected. This is the reset point, this is pulse point. Here the count name, this represents name of the counter. This is the number of pulses counted by counter. This is here also counter used in the ladder diagram. Okay, this is the, see here example, here counter is connected. Okay, so this is the, this whole thing is the ladder diagram. And here see, one example is shown here. This is a bulb for like for means for growing a ball by using PLC, we can for the controlling the lighting of this ball by using PLC, you can control the illumination of the ball. This is another one example just given here. And the next one is the timer. Timer, it is an instruction that waits a set amount of time before doing something. So type of timer is the one delay timer and on delay timer and off delay timer. So on delay timer simply delays turning on. So after sensor input turns on, wait X second before activating a solenoid valve or output. So this is the most common timer. It is often called T-on, timer on delay, and timer, TIM or TMR, timer. These are all the notification. So off delay timer simply delays turning off. So after sensor or input sees a target, it turn on a solenoid or output. So when the sensor no longer sees the target, it holds the solenoid on for X second before turning it off. So it is called TOF, timer off delay. Okay, need to know two things. What will enable the timer? Typically this is one of the input, a sensor connected to input 000 for example. Okay, so how long we want to delay before we react? Let's wait 5 seconds before we turn on a solenoid for example. Okay, so this is the timer given here. Okay, so on delay timer is the T-XXX is the timer name. When the enable input is on, the timer starts to tick. When it ticks, these 5 Y's, the present value, these 5 Y's times, it will turn on its contacts that we will use later in the program. Okay, so timer in the ladder diagram looks like this. This is the timer connected here. This is the name of the timer, and this is the times the timer ticks. Okay, so see, wait for input 001 0001 to turn on. Timer T000 a 100 millisecond increment timer starts ticking. It will tick 100 times. This is written here 100. So each tick is 100 millisecond. So the timer will be a 10,000 millisecond. 100,000 millisecond. That means 10 second timer. So 100 ticks into 100 millisecond is equal to 10,000 millisecond. So when 10 seconds have elapsed, the T000 contacts close and 500 turns on. So when input 0001 turns off, false, the timer T000 will reset back to 0, causing its contact to turn off, become false, thereby making output 500 turn back off. Okay, so this is all about your timer and counter. Okay, so here you are studying about the ladder diagram using timer and counter. Okay, so this is all about the details of ladder diagram and and description of contacts and coils, then ladder diagram using timer, using counter. Okay, thank you.